Thanks. So I'm absolutely delighted to introduce Venky. Venky knows a few people in this room already, actually from ITC days. So Venky is currently director of the Centre for Quantum Research and Technology at the University of Oklahoma, and you'll notice that he's spelled centre wrong. So we don't know about that, Venky. American.
Yeah.
Now, I want to say Venky started his research career at Bell Labs. And as we all know, Bell Labs invented everything that is of any use that we use today. It's quite extraordinary. So he was equally inventive at Bell Labs. And it was from there that he went to Rutgers and started work on pulse laser deposition. And Venky then created a company called Neosera, which has been fantastically successful. And it was at Neosera that we all learned how to make pulse laser ablated high temperature superconducting thin films, which Venky pioneered, and which Peter Petrov and myself then started using. And of course, Norbert Klein was involved in the ITC game as well. And so was Professor Leslie Cohen. That's right. Leslie Venky then spent 10 years in NUS in Singapore and set up a quite remarkable lab out there, and again spinning out companies. He returned to the US to take up the appointment at Oklahoma, and I have to say, along the way, he's picked up so many prizes and awards. It's quite extraordinary. Just take a quick look at his CV. It's amazing. A couple of years ago, he was made a fellow of the Royal Society. That's an enormous accolade. And so I'm absolutely delighted to welcome Venky and to let you get on with your talk. Thank you very much.
Thank you. Actually, coming to Imperial is like coming home for me. This is like home away from home in England, basically. So I love this. So thank you. Today, I'm going to talk about members of the Neuromorphic circuit, but I'll also give you an introduction to the center at Oklahoma. This is our center. This brand new building was constructed just about 3 years ago. It's cost about $35 million to build this. It's a very state-of-the-art laboratories and buildings in the air. This is a quantum center. And to give you an idea of my journey, I started at Bell Labs in 1973. Probably many of you guys weren't even born then. Anyway, so I established an ion beam mesotaxi laboratory there. And then in 83, the Velcro was created, and where I essentially created a high-TC microelectronics network involving many corporations and a number of universities. And then I established a Center for Surface Modification and Drug Research. And then I went to NUS to create a Nano Institute there. And now I took over as director at the University of Oklahoma Quantum Center. In the last year and a half, I've created a new center for what I call advanced materials. It's called Center of Optimal Material for Emerging Technologies, COMET. I always wanted to create a center named COMET, and this title fitted in very beautiful. So that's where we are. So you can see my life has been about creating centers, and part of the ability to create centers means you have to work with very high ego people and getting them to work together. Okay, and how do you make them work together, right? And that's so I've learned a lot of tricks in Bell Labs, where I was always surrounded by people with, Mount Everest type of egos, and figuring out how to work with them and survive there was taught me a lot of things actually. So this has been a big piece of the creative center. So the CQRT structure, we have right now, as of today, I've recruited after going there, about 5 new faculty members. So we are roughly approaching about 18 faculty members in the quantum center. And I've created a small quantum engineering group along with this stuff. And so this is progressing really well. So the University of Oklahoma itself is based on 4 strategic verticals, aerospace, defense, and global security, environmental, energy and sustainability, future of health, society, community transformation. And we have a lot of what I call horizontals that go with this. And these are like the security, our security overlaps extremely well with all these 4 different verticals. And in addition to that, there are about 5 or 6 other institutes there, which also, cut across good verticals there. And here's the quantum materials group. We have an MB lab for 3-5 growth materials, and this is Hanjon Pei, whom I recently hired from Cornell. He's from the Paradigm Center there. He's an oxide MB guy. So we're setting up essentially an oxide. This is the lab that we're setting up, which will have many PLD systems there. Also all the measurements, electronic, electrical, magnetic, etc. And then right here is a small laboratory where we're going to do breathomics, which is essentially breath correlation with diseases. So this is the basis of one of the companies we started in Singapore. Right. So then this is the quantum sensing group, and the quantum sensing group has more people in it, but they're unfortunately not in this picture here. But they're working on essentially cold atoms and using them to make essentially atom interferometers, atom-based gyroscopes, and all kinds of really cool stuff. Just amazing, these labs. I mean, you can go in and see these cold atoms just suspended in the middle of the lab. You see this thing, and it's just like really awesome, actually. And then we have this is the quantum optical communications laboratory. I mean, personally, I think in the quantum area, before a realistic quantum computer comes into play, my belief is that quantum optical communication is going to become more important because of the cybersecurity component. Second one, of course, quantum sensing, and quantum metrology is already there, is making it way in a big way. I mean, it's pretty mind blowing what's happening in quantum metrology, because they can literally today measure if you move an object from here to here, and effectively the gravitational time difference that creates can be actually measured. It's like what 10 to the power minus 15 or something like that. Some ridiculous number which you can measure today. And this is there's a photovoltaics group and primarily focused on things like the organic perovskite. So we're building a very strong tie with a number of groups, primarily in India with a number of the IITs, and these are a lot of joint collaborations. So this is kind of my dream. Currently, our center brings in roughly about $2.5 million in research revenue. We want to go to roughly about $15 million in about, let's say, I'm sort of talking about like 5 years' time, and increase the number of people from roughly about 80 people right now to something like about 200 people. So that's kind of where we are going. This is our quantum center, and in the basement of this physics department is the Comet laboratories are being established, and they will be addressing a variety of materials related issues. And roughly there are about 25 faculty members from about 8 different departments, and they span all of this stuff. And so these are kind of like, this is more or less a quick introduction to what's happening at Oklahoma. Okay, so yeah, so now we come to the talk, which is what you've been waiting for. All the boring stuff. Okay, that's over. Okay, so now question is, there's a rationale for building low switching energy memories, and the question is why? Why do you care? And essentially, these are very important for basically neuromorphic circuits, and I'm going to give you that rationale immediately. For example, we just calculate the power consumed by all human beings. Our brain, which does so many things, right? Most of us, blame ourselves, say, I'm not smart enough, et cetera, et cetera. An average human being is actually very, very smart. And you try to build a computer to do all the thing an average human being does, you will find it very, very difficult. Okay, so average human beings are smart. So we all have to pat ourselves on the back. But you know how much power a brain consumes on the average? Only 20 watts, basically. So with 20 watts of power, we get to do a heck of a lot, right? So you compare yourself with a computer in terms of power consumption and say, hey, how much I can do, For example, the Blue Gene IBM computer beats a guy who's an expert in chess or whatever, right? Chess grandmaster. But then the chess grandmaster uses 20 watts of power, and the IBM computer uses terawatts of power. That's a big difference. To be able to beat a human being, you need that kind of power level. But anyway, I kind of calculated the total power consumed by the, essentially human beings all across the world, 8 billion people, I assume. And I made a couple of assumptions that, people are consuming the same power while sleeping as well as they're awake. Okay. And I also dropped out our former president out of this calculation because that completely throw off these numbers, And in comparison, look at the power consumed by data centers in 2016, right? Is roughly 3,000 times more power, and actually 20% of the global power will be consumed by just data centers in 2025. 25% of the energy produced in the world will be consumed by data centers. So essentially by about 2040, there won't be enough energy left on Earth to essentially power all these data centers. Okay, so we really got to lower the energy consumption of electronics. So that's really one of the key things. And interestingly, that 50% of the power is consumed by memory. So if you can make memories work efficiently, then you'll have a heck of a savings rate just right there. But then we're hearing a lot about today about artificial intelligence, machine learning, and companies are making out what are called biochips. And biochips are now coming out almost like potato chips now. I mean, basically, every company is introducing their bio, but they all have a problem because they're all based on silicon technology, CMOS based thing. And CMOS technology has a fundamental problem called the von Neumann body. Okay. And so what happens is the CPU from the memory are spatially separated. Okay. And so what happens is in all our circuitry, I mean, basically the way conventional computers are organized, there's a huge amount of time involved in just moving data back and forth between the memory and the CPU. And if you look at something like, performing, AI ML type of operations, actually the amount of energy that's consumed by the CPU is a very, very, very small fraction compared to the total energy expended in just moving the data back and forth. So this is a huge disadvantage of CMOS. And so CMOS is not the solution for AI ML. You need a different technology completely. Okay, so that's the reason why people are excited about things called memristors. And memristors are devices which have both memory as well as the operations in the same device. Okay, so the whole world is shifting towards what's called in-memory computing, and the memristors are ideal for in-memory computing. Okay, so in the silicon world right now, they're all trying to emulate in-memory computing by trying to bring memory and the thing as close as possible into as good a close proximity. But as you can imagine, it's impossible to get a million devices and million memories right on top of each other unless you can really put it on the same device, right? So that's going to be a big issue. So the neurons do exactly that. In a single neuron, basically, is a CPU. It's also the memory. Okay, so essentially everything is co-located in the same place. Neuron does so many amazing things that I doubt in 100 years we'll ever be able to replicate a neuron with an artificial system. But aspects of neurons we can imitate and and emulate, and those are the kind of devices we're making today, neuromorphic computing. Okay, so so what are the so I'm going to give you a few examples of oxide approach to low energy memory. Okay, so there are basically create like capacitor-like structures, okay, and you put some material in between, it could be an oxide, and then essentially there are different mechanisms by which people are building what are called resistive devices. One involves oxygen vacancy diffusion. Then there's something called band gap renormalization, which is an idea that it was discovered in my group, and then ferroelectric tunnel junctions, and then also metal insulated phase transitions, like for example, vanadium oxide is a very classic example of that. Okay, so there's a whole bunch of technologies that people are investigating. I'll just give you a sample. I don't want to go through all of them. I'll give you a sample of just ferroelectric tunnel junction, how they work. Okay, so a ferroelectric tunnel junction basically consists of essentially a bottom electrode. Then you have like a ferroelectric layer, and then essentially you have essentially a top metallization. So this is, for example, it consists of there's a top metal like chromium gold here, and there is this barium titanate, which is a ferroelectric layer, and they insert some, the aim of these experiments were to insert some magnetic materials here, like a LSMO, which is a ferromagnet. Then you have essentially bottom electrodes are like conducting layers underneath. And you get essentially, if you look at this transport property of this capacitor, you get the resistance versus essentially applied voltage. You get this very nice hysteresis curve. And you can sort of see that the on ratio to the off ratio is actually, this is really the higher conductivity. This should really be on and this should be off. But anyhow, the ratio here is like almost 100 or so. And he found that actually by inserting many, many layers in between, this on-off ratio can be, 10 to the 5, 10 to the 6, it's like a big race for trying to push this ratios up. So we in fact did a study where we actually created these layer structures. And I'm giving you an example of 3 different devices here. The simplest device consists of just a metal, then barium titanate, and then bottom electrode, which is a conducting oxide at the bottom. Okay. Now we insert sort of another oxide layer here, and then we insert, say, 2 more layers here, 2 different composition of oxides, and see what happens, right? And then what you see is that, you get, if I compare these 3 different devices, this is the simple device, the simplest device. You can see an on-off ratio of roughly about 10 to the 2, and then you add 1 barrier layer of 10 to the 4, and then you add 2 barriers, like 10 to the 6. Very interesting. Then, if you look at the switch-on voltage, in all the cases, the switch-on voltage is the same, and the saturation voltage is also the same. So obviously, doesn't matter how many layers you put in, it's a ferroelectric layer that controls the whole switching operation base, And on the other hand, if you look at the resistivity in the off and on region, so if this is the on and this is the off, you can see that the on state resistivity changes very, very gradually as they increase the number of layers, whereas the off state resistivity, on the other hand, actually changes much more dramatically. This is the reason why we get a very large on-off ratio in these kind of devices. So anyhow, that gives you an idea. And we started exploring things like how many ferroelectric layers can I insert as a barrier, okay? And so here, for example, we are able to go down in this curve. You can sort of see the number of the unit cells of the ferroelectric layer that I can put in and still get, a hysteresis group. We are down to about 2 unit cells with barium titanate, and we have now gone to bismuth ferrite, and this is actually 1 unit cell of bismuth ferrite, and you can still get a tunnel junction. This is interesting because for a while there was this crazy notion around that, for a ferroelectric to recognize that it's a ferroelectric, it must have a minimum of 3 unit cells. This is like some theoretical postulate, right? And there was really no basis for it. And we experimentally showed that even a 1 unit ferroelectric behaves like a ferro. So there's no magic there. Interestingly, you can actually look at other oxides. For example, I'm going to compare here with the barium titanate with strontium titanate. Okay, in strontium titanate, there's no ferroelectricity, but you can see that again, R versus voltage, you get a very beautiful hysteresis curve with this strontium titanate. And this is purely arising from oxygen diffusion, basically. Okay? And so this is the diffusive behavior, this is essentially ferroelectric behavior. And they're completely different voltage dependence, thickness dependence, and so on. So for example, this is essentially, you can see, this is barium titanate, it's completely, sort of like thickness independent. Whereas in the case of strontium titanate, there's an inverse thickness dependence. You can see very, of the, the voltage where it switches. Right? So there is a ways you can clearly distinguish between the two. In fact, if I take the barium titanate and go to slightly higher voltages, I can now see the diffusive behavior. The oxygen diffusion creates a separate switching. And this switching here is actually from oxygen diffusion, and this part is actually arising from, ferroelectric behavior. So you can see both type of behaviors in the thing. So, it's very interesting how people use these memristors in a AI to actually solve AIML type of problems. For example, matrix multiplication is a very natural thing where we use to create like a circuit, and you will be able to, so like it's called a crossbar array. You use this crossbar array and you can solve matrix problems very, very easily with these things. And the emphasis right now is, so at each matrix nodal point, there will be one memristor sitting there. Now, what people want to do is actually change the weight function of the memristor. So you can sort of see how it works. So you have an input current comes in, okay, that goes into the crossbar, okay, and then the bottom of the crossbar, you pick out the currents coming out of the crossbar, okay. So you're just using Kirchhoff's law, basically. So it's a current times the resistance of that memristor, okay. And then the next one, the current times the memristor, you're just adding up all the current times the resistance of the memristor, and that'll be your final output, which is exactly like a matrix. You add up the elements of the matrix. Okay, it's exactly the same. It works like that. But in building an AIML circuit, what you really want is you want to start off the matrix with different weight function for the matrix elements. Okay, and then you train the circuit to do something. Okay, it could be, for example, voice recognition, image recognition, whatever it is. And in the training process, what happens is you reset the weights of all the matrices, and that's a training process for an AIML circuit. And so what that really means is that you need to have not just one resistance value, you want multiple resistance value for each nodal point. Okay, and that's where the name of the game right now is. Everybody is really working on, trying to create, these type of memristors where you can create multiple memory states. And so, I mean, the record right now is, I think, 1024 from the University of Southern California. And it's actually in an option-based system, they created that many steps. And my collaborator in India, this is my former graduate student, now a professor in the Indian Institute of Science. He has now created a system where he claims about something like 10,000, 10,240 steps that he can do very reproducibly, which is pretty amazing. I mean, if we can get to these things to be practical circuits, it will be very, very exciting. We're now at a point where almost all these universities are making their own circuits. You can actually, you build your oxide circuit, you can send the design to TSMC, and the TSMC will make it free, essentially, mass produce it. And right now, Tsinghua University has got 2 circuits, Delta's got 1, University of Southern California, they're preparing their one. So like that, every university, hey, I got my own circuit, so everybody's excited. So I want to create an AI/ML lab in Oklahoma where we're in the process of doing that, where we want to get these circuits from all these different people. We want to evaluate them to see which one does what better, and that sort of thing. And we also want to create a sort of a lab where, students will be encouraged to think of problems to solve using these kind of what I call neuromorphic circuits to see what are the problems that you can solve practically. And I expect to see a lot of spin-off companies coming out of that idea. Okay, so this is the controlling the option diffusion in a barrier is the way people are actually building these wave functions in this memory space. Okay. So one other thing I want to tell you quickly is like, so how do I create a barrier layer in which I can control option diffusion the way I want? Okay, you can basically create a barrier in which I can change the composition of the barrier at atomic level. Thereby, the option will have different diffusion coefficients, say layer by layer, let's say. Now, how can I build such layers with accuracy and control? Okay. Because when we make films, we don't have control on the composition that much. Okay, we have some control, but not to that level. So we've now developed a technology called low angle X-ray spectroscopy. I want to change the name. Lax sounds a bit like laxative. I want to get a better name. It doesn't sound so good. So I'm telling everybody, hey, listen, change the name. Get a better name. You got to come. Anyway, it's an in situ composition analysis technique. Okay, so the way it works is you have essentially when we do read, which is a reflection managed electron beam, we bring an electron beam, bounces off of the substrate, and then goes off. And this enables us to measure the structure of the film as the film is being grown. We can actually measure the number of layers, atomic layers that we're growing using read oscillations. So read is an integral part of our film growth process. But this electron beam, when it strikes the film, also generates X-rays. And these are all X-rays, which are characteristic X-rays from film, substrate, everything will all be coming up, right? So essentially, there was a program organized by the Navy about 20 years ago, a guy named Cooper, he gave money to a lot of film groups and said, figure out a way how we can use this X-ray to do in situ composition. And everybody tried, nobody succeeded. And part of the problem was because, so part of the problem was because of the physics. I think that's like I just lifted up and hang it up. Anyhow, so I'm pretty sure they're gonna call it. Anyway, the point is, so I gave this problem to my people in my company. If you solve this problem, it's going to be a big deal, right? I had a Russian guy who's unfettered thinking, one of those guys who really thinks very originally, Misha. So Misha came up with a complete beautiful solution. So the way it works is like this. So here is the X-rays actually collected as the film is being grown. So you can sort of see this is the Bremsstrahl level, which is like the background in the X-rays. And you can see a lot of peaks. And these peaks are the characteristic X-ray peaks of the films and so on. So the problem with X-ray spectroscopy is that, right, if I take a finite thickness of film and look at, the X-ray that's coming out, this X-ray is subject to absorption by the layers above. So the X-ray coming in from the bottom layer is absorbed by the layers above it. And therefore you have to correct for it. And you don't quite know how to do that, in an easy way. Okay. So what we do here is we basically select the elements of interest to us. Okay. So, and then we watch only in that those elements as a function as a film is being grown. So you can sort of see that there's two different elements that we picked here. And they're growing, and you can see the ratio of these elements is changing as the film thickness is increasing. Okay? And that's because of this correction factor. Okay, so because of the fact that there is a layer that's absorbing above, and you have to correct for it. Right? So what we do is we let this go for a little bit, and then we just extrapolate this to the origin. These data, we take this data from here, we extrapolate it, we asymptotically extrapolate it to the origin. Then that ratio corresponding to zero thickness gives you the correct composition. So that's it. Okay. So this is done roughly right now. every about like 20 nanometer of film growth. Once 20 nanometer film is grown, we can immediately get a composition on the screen, So we actually compact this now with so this is the X-ray data for various films. In this case, is lanthanum, calcium, manganese oxide. And this side is actually Rutherford backscattering data, okay? So we send this film to Charles Evans in West Coast. It takes roughly about 2 to 3 weeks, and we get the answer back here. So this is the composition after 3 weeks from RBS, and this is the composition as the film is being grown. So this is you see the composition measured by this technique with respect to RBS, which is the gold standard, almost within 1%, which is extraordinary. I mean, I showed this to Data Flow, and he said, "Holy mackerel!" And this worked for MBE. I said, "Yeah, it works for sputtering, but we'll have to demonstrate it for MBE." So this is, for example, this is one of the programs that we're going to be developing under the DoD Commons program, the semiconductor development, where the industry is very interested in this. The companies like, so what is happening with PLD now is like, all of a sudden, PLD was purely an R&D thing. And recently, there was a company called Soulmates, which made a production PLD system for 8-inch wafers, production online thing. And that company was acquired by Lam Research. Lam Research is the largest semiconductor equipment manufacturer today. It's larger than Applied Materials, actually. Applied Materials is the number 2. And so Lam actually bought this thing, and they now think that they want to now put PLD in production, semiconductor production, because ferroelectrics are now becoming part of the next generation circuits that are going to be used. And also optoelectronic materials like barium titanate and so on are becoming very important for silicon photonics. So the variety of reasons why oxides are becoming important in the silicon industry now. Okay, so that's one of the interesting things that's happening. Okay, so there are also bio approaches to neuronal circuit. This is kind of one of my dream projects, and what I really want to do here is to actually see if I can build a live neuronal circuit, even a small circuit, like say 3 by 3 neurons, 2 by 2 neurons. If I can do that and I can measure electrically the circuit, we'll learn a hell of a lot about how neurons really communicate with each other. Okay. And it's not an easy thing to do. So, so that's why we're working on the project. And how do I do that? Okay, one of the problem is to figure out how cells grow on various surfaces. So we prepared what's called a combinatorial material surface in PLD by say 3 different, let's say, I want to make a composition with say 3 different materials. We just rotate them in the sequence that I showed you right now. So now I've got like this is like a ternary phase diagram. Basically, you can see it's like a triangular phase diagram. At the apex, each is a different material, right? So on this, I can put a PDMS layer and create little cells there, and I can grow within those little compartments, bacteria and cells, all kind of stuff. So we can do interesting biological experiments to see do cells care about what surfaces they grow on? Okay, and it turns out that here's the human neuronal stem cells, and this is the binary phase diagram. On the left side is all yttrium oxide, on the right side is all zirconium oxide, and you can sort of see that the cells really don't like to grow on yttrium oxide. Nothing grows on yttrium oxide. Where as soon as I increase the percentage of zirconia to some value, say 10%, boom, the stem cells really start growing very beautifully at the surface. If I take the fibroblast, which is your most dominant cell in your body, which is like in all the muscle tissues, you can sort of see it takes roughly about 50% of concentration of zirconium before it takes off. And this is what it's a different cell called keratinocytes, and these show a completely different kind of a behavior. We now have a mathematical model for why these cells grow differently on all different surfaces. That's to do with addition and so on. But this tells us I can now create surfaces in which cells like to grow, surfaces in which cells do not like to grow. So if I can create like a checkerboard pattern, I can make the cells grow only that I want them to. Right? So that was the idea. And what was even more interesting was if you took differentiated stem cells, the differentiated stem cells grow almost like, 200% more efficient on these surfaces compared to standard laboratory surfaces. And so this is the basis of a company we formed called Cellivate, which is now, marketing artificial meat, artificial tissues, implant coatings, et cetera. So it's a different company working on this. So this is a company that we're collaborating in California called Neurosyntek. These guys are actually trying to grow. They want to take humans, their neuronal cells, various sensory cells, and actually put them into real use. And they figured out a way to keep these cells alive for a very long time, by months. I mean, they keep them alive for months. And they built this electronic circuit with metallizations. And they've also figured out how to make ohmic contact to these cells. And it's a very, very interesting process in of itself. And the big problem is you can see the cells are all over the place. They just don't grow where you want them to. These are neuron cells. So one of my thoughts is that if I use these different oxides, which allow the cell to grow, the ones that prevent it from inhibit from growing, combination of these, I guess somehow forces the cell to go only when I want them to. So I can, and the other interesting thing about these cells is these cells have essentially, they have these dendrites, and they also have this little sheath of this cell, and they interconnect to each other. And there are simple lithographic ways on a surface you can cut grooves, and they will automatically go in those appropriate directions. Cells are oriented in the right way. So there's a lot of different things involved in nanotechnology, surface science, everything that's involved in making this work. And this is going to be it's not something that's going to happen in a very short time frame, but is one of the things that I'm pursuing, ideas I'm pursuing. The last part is actually there's a very exciting organic approach to ultra low energy memories, and essentially this work was done by my former student. His name is Srito Goswami. Brilliant guy. I mean, I've had about more than 60 doctoral students, and I put this guy like in the stratosphere. He's really just an amazing person. Anyway, this molecule is very interesting. It's got ruthenium at the center, and it's got 3 ligands. Okay, so you can see this is one ligand, there's another one, and this other one. This ligand is called a phenyl azopyridine, and essentially this, 3-dimensionally looks like a butterfly with 3 wings. Actually, if you look at it from the side cross section, it looks like a Mercedes-Benz sort of sign. And you put the stuff, you spin it onto a substrate. The bottom is the indium tin oxide layer, and then you put this brown stuff with this phenomenal material, and then you put a metal electrode on top, and this is your device. You measure them right across. Surprisingly, you get this amazing behavior of the current density versus voltage, where this is like 321 devices of different dimensions and several number of them, and all of this is the cumulative data put together here. So the fuzzy thing that you see is the spread among the data of all these devices. And you can see the spread is very small compared to the separation in the resistive state, right? So that means the probability of error for this device is actually in this batch, it's like, 1 part in 10 to the 13. That's, how ridiculously reproducible these devices are. What is also interesting is, if you look at the real star in this molecule is this azo group, basically the N double, there's an N double bond N, this is called the azo group, and this is the guy that's a champion that's making this device work. And that has to do with the fact that this azo group has got basically 3 charge states. Okay, so one where it's neutral, and then one in which you lose an electron, and then you lose 2 electrons. And essentially, you can, for each of the state, there is a corresponding Raman spectrum. So this is basically 0, and this is 1, and this is 2. Okay, 2 ionization. So using Raman, I can actually look at the device at different stages, and I know exactly what's going on. So in this device, okay, let's look at this state here, at this origin here. You can sort of see that there's 1 unit of 0, 2 unit of 1, and then There's nothing in two. So the device is actually in 1, 1, 0. The three ligands are 1, 1, and 0. When I go to this point here, 2, you can see that this is now suddenly the 0 has become double the size, and 1 remains a smaller unit, and so it's 1, 0, 0. And then when it switches, and I go to this point 3, you can see all the peak is under 0, and there's no 1 or 2, and so this is 0, 0, 0. Similarly, this is 1, 1, 1, and this is 1, 1, 2, and then when you bring the voltage back, come back to 1, 1, 0 basically. So the interesting part is, why is it that all the on state, in other words, the higher conductivity states, all the ligands are in the same redox state, 0, 0, 0 or 1, 1. But the moment one of the ligand is in the wrong state, the resistance becomes very large. Okay, so this really has to do with the hopping. So if bottom electrode, electron starts hopping, it goes to the first molecule, hops to the second molecule, third molecule, keep electron is jumping from molecule to molecule, right? And what happens is that the conduction band, or in the case of molecule, we call it the LUMO levels, they all only line up if all guys are the same, for example, it's easy for an electron to go from 0 to 0, but not 0 to 1 or 1 to 0. Okay, it doesn't work. Okay, so you can sort of see that if probability of this guy is going to be, since at least one is different, one thing is different, so it's going to be roughly 2/3 of the hopping probability compared to this guy, 0, 0, 0. But then 2/3 to the power of say 40 hops is a very small number. That's why when one of the ligand in the wrong state, the resistance is very high. Okay, so the other very interesting things about the molecule, they have these so-called counter ion, which is added in and these kind of stay right next to the molecule at a very short distance away, and they occupy very special spatial pockets, and they give you the inertia. So when the device switches on, when I turn it off, it doesn't come right back at this point, but it just hangs in there because these so-called, the counter ions give it the spatial rigidities or inertia, basically. And so, the interesting part is when you increase the electric field, both the top electrode and the bottom electrode, an amazing thing happens. The switching voltage, so the way you do that is we can put nanoparticles on the bottom electrode, and the nanoparticle will cause enhancement of the field. Okay, and then for the top electrode, we can bring in AFM tip, conducting AFM tip, so that the field is enhanced. When you do that, you literally go from like 4 volts switching volts, 4 volts to down to about 0.1 volt, basically. Switching volts really shrinks all the way down, and the current density really jumps up by orders of magnitude in the device, which is really the way you want it to go, because you want to make the devices smaller, and it begins to perform even better when you do that. So here are, for example, nanostructured electrode. The molecules everywhere, but only where the field is high, the devices are switching. You can see right here, where the nano pattern electrodes are right below here. And these devices are remarkable. I mean, they are, we do a read-write sequence, and we repeat this many, many, many times. And you can see, if I did this to, let's say, your flash memory, right? You can do about 10 to the 6 cycles, and then your memory will start producing errors. Look at this guy. We've gone up to 10 to the 12, and all the memory states are flat. No error, nothing. I mean, I've never seen an organic memory do something like this. These are operating at like 80 degrees centigrade for 3 months, and the memory states are absolutely rock solid. I went to my friends in Intel, and they gave me this ITRF roadmap for about 2015 or so, and we compared this for memristors, and this device just beats every characteristic. It literally just completely beats every one of them. Today we have made a device that essentially, it switches basically with a switching voltage about 70 millivolts. And it's essentially 1 atom joule is the switching energy of this device, which is really, really small compared to, most devices. And we can actually patterned this device down to almost like 7 nanometers. And the diameter of this molecule is about 1.5 nanometers. So I think realistically, the smallest device we can build is maybe about 3 nanometers with this device. This is what we think we can do, you know. And the essentially there are this we can do a slightly different ligand in a similar system, and you can get multiple memory states. And these devices do some extraordinary things, like they have memory in the capacitors in addition to the resistance. And this leads to devices that are behaving exactly like neurons. So neurons do things like integrate and fire. What happens is that in a neuron, basically, signals are integrated, this is the input, and then a neuron will fire once it reaches a certain threshold. So you can see this kind of a behavior you can see here, integrate and fire for a continuous stream of input. And you can control this firing interval by changing the load resistor. And we can also do what are called potentiation. And then there's this amazing thing where you can build a self-oscillating circuit. And as you change the load line, basically this oscillation eventually goes into total chaos, chaotic regime. And these are all characteristics of neurons. I mean, neurons have, you know, this behavior of chaotic behavior, and there is actually a way to actually help us preserve our neuronal system. If the neurons in our system start synchronously acting together, then you get epilepsy, you get all these problems, right? And those are all arising when neurons suddenly go into some kind of a resonant behavior, and you don't want it to happen. You want to have a little bit of noise in the system, some chaos to prevent it from happening. So this is the devices do this stuff. And most recently, we came up with another version that we replaced the ruthenium with the iron, and you get this amazing device which has so many different characteristics on this side of it that essentially what this means is this device can lead to something like 73 different decision possibility in a single device. And so this is called a decision tree. And you can use this to do, you know, an AI ML functions. And so we've actually built an actual circuit with these devices. And these devices are very, you know, durable and consistent, you know, there's multiple devices. And we've compared them to what I would call real performance with competing circuit built at Delft and other places. And these are the actual performance comparison where we see that this red line is our devices. And these things essentially roughly about 5,000 times better in terms of the energy bandwidth product of these devices. So these devices are about 5,000 times more efficient than the world's best circuit built by the Delft group, basically. So anyway, so that in a summary, this is our team of the various people involved in this, and this is the so-called genius that I was telling you about. He's now a professor at Indian. Even the whole team was supposed to come with me to the United States. Indian Institute of Science intercepted, made this guy an offer he wouldn't turn down, a startup package of $3.5 million, and for India, I think that's probably a record. So this guy is in a whole floor for a laboratory, and so he's very happy there. So anyhow, so these are our various publications in this area, and so with that, I'd like to say thank you.
So I think from the LCN perspective, it's really great to see how you've been able to bring people together across your various basic career steps. So this is also something that hopefully we can work on and look at the initiatives and quantum and materials and so on. So lots of synergies there. And thank you very much for the overview of the Memristor work and the PhD work, and this is definitely something where we can take a lot of questions. Yes, so please, yeah. Leslie,
Is that me?
yes, absolutely.
Well, first of all, I have a suggestion for your labs. Because I think if you call it logs,
locks.
Yeah, those of you who know about smoke salmon, I think you're bringing up all different communities. People
is it?
say
How do you
it's
say?
not
LO?
it's
LO?
not lots, it's a type of smoked salmon.
LOX. Oh, okay. Okay.
It'll go down another.
Locks, yeah, locks, I mean, yeah.
Anyway, that was just it.
So what is it all for? What do they, so in the locks, and what does the O stand for?
Well, I think Russian actually is a form of. We can talk about it.
All right. Okay, lunch would be perfect to talk about locks. Yeah.
Question. The 3 nanometer device, is it scalable?
Which one?
Your 3 nanometer.
You mean this organic thing?
Is that a scalable, is that a viable technology?
Yeah, I think so. It's a viable technology. The question really is, would the industry adapt to this style of, making the devices? Right now, the memristive technology is really driven by the oxide community. And the oxide memristors have really bared every company, Samsung, TSMC, they all invested, multi-millions on this stuff, right? So for them, it'll be really difficult to suddenly jump into this organic stuff, right? And so anyway, I bought all the patent rights to this from NUS. So, I've put my own personal money behind it. So I think there is I believe in its future. So we'll see where it goes. So.
But I did want to ask oxide versus organic, which is the more promising technology, but you've answered that. It's my third question. So
Right now, in terms of performance, the organic beats the oxide hands down. Because in the oxide devices, the big problem right now is no two devices are the same. They're not. Because what really happens in an oxide memristor is actually there's a lot of interface chemistry takes place. So what they do is they to make the memristor work, they have to do what's called a forming step. So in the forming state, they use a much higher voltage. And what it does is essentially it drives the metal atoms into the oxide and so on. So you actually have some kind of an interfacial mixing there. And so the final structure of the device is something that you don't even know what it is, but it's some little, filamentary stuff that are all, these are not actual metallic stuff that are protruded into the barrier region. Okay. And therefore they're not identical for each devices. So that's one of the problems right now with oxide memristor, because there's a lot of work of corrections that are, correction codes that are developing that takes up a lot of the energy basically.
okay, so my middle question is speed for the organics compared to the inorganics. What is I saw microseconds on that foil that you showed. What is the speed of the on-off?
Okay.
Obviously,
The measured speed is about 5 nanoseconds, but that is primarily because we are limited by our circuit. We are using still twisted pairs, basically. This is not the way to measure it. You have to use the SMA connectors and so on and so forth. So we are right now working with a group that can go down to about like they can measure electrically things down to about less than 100 picosecond. So we're working with a group to measure the actual speed of this device. I think I'm estimating it to be less than 500 picoseconds. It's got to be the hundreds of picoseconds based on the RC time constant. Yeah.
On that, just because these changes in your azo groups, they can also be done optically, right? And there's been some optical switching there. And is that speed is that speed something that we can take to look at the limit of the voltage switching?
Yeah, it's possible. I mean, that is another idea that we are working on. It turns out that this particular one of the molecules that we're dealing with, the ruthenium, phenylazopyridine, or RUPAP as we call it, and that has actually an interesting property that in the off state it's photoluminescent, whereas in the on state it is not. So essentially, it's a little bit very interesting because if you build a brain-like circuit, actually, you can tell when it is on and off because by measuring the photoluminescence, you can tell which device is turning on, which was not. And that could be one way for us to actually make that measurement. Yeah, we'll be doing that actually.
Okay.
Yeah.
And then, but well,
Cheers, that was great talk, thank you. So when you're designing your neuromorphic circuits at the end, to what extent are you like taking into account like the physics of the different systems to build the circuits? Like, does a memristor, an oxide memristor circuit have to look quite different from an organic memristor circuit, or is it basically just the same circuit but with different?
Actually, right now, this organic memristive circuit is completely different principle, and also the way you have to use it in computing is also very different from that of the oxides. And that is actually a problem for us because, you don't have a large community of people who will work with you to develop the, the software and other stuff, right? So so when you develop something radically different, you run into a problem that there are not too many people working with you basically, and they don't have the expertise to do that. So that one negative and a major issue for us right now. So, yeah.
Well, amazing talk. So my question is more general. So I think if you want to transfer any new memory technology from the lab to a real application, the scalability of the technology and the yields, production yields, and so forth. So what are the techniques, the growth techniques, which you kind of prefer, both for the oxide and the organic? I thought maybe it's some ALD, and for the organic, it's some spin coating. So I mean, have you thought about which kind of production method you could use?
Yeah. For the organic, it should be a spin. Right now, yeah, that's what we should do. But right now, that's not how we make meat. So we do what's called drop casting. That's how we do it right now. In fact, we haven't figured out. We're not really experts at trying to come up with the right kind of solutions and everything to make it spinnable, for example. Right? We just do drop casting on a spinning disc. You just drop cast it, and then it just prints there.
So I mean, the beauty is
off center.
Which are compatible with steam out there.
Yeah. So we need to develop a scaling process for this. So we need to develop a way to coat this uniformly over large areas. That's one. We need to develop that. Secondly, we need to develop actually lithographic processes. Right now, we're demonstrating, it's conducting AFM to show that it can go down to, 7 nanometer dimensions. But the ultimate device has to be actually patterned, right? And so we need to really develop the lift off and those kind of processes for it. The conventional photoresist technique that we use actually damage the molecules right now. So we need something completely different kind of a process to pattern these things.
Even we ask for the oxide, it's normally, if you do PLD, it's normally pretty high temperature. Is it ALD which you kind of consider, because that's a kind of standard in the semiconductor industry?
Yeah, so I mean, for the layer thicknesses needed for many of these memristors and so on, ALD would be perfectly good.
Yeah,
sure. It definitely be good, and even PLD would be suitable if the production.
In spite of high temperatures.
Pardon?
In spite of the high temperatures which you have, because that's always, the deposition temperature for the oxides are normally a couple of 100 degrees, aren't they?
Yeah, generally for the so-called the oxygen diffusion based mechanism, right? Many people don't even use single crystal oxides. They actually use multi-phase material basically. And so you really don't need to have very high temperature for the memristive application. Because you have metal, and you put the stuff and another metal layer. So you don't want very high temperature process because the metals will react.
Molecules could be sublimed as well, maybe.
Pardon?
Molecules could be sublimed as well, maybe, and then you've got a whole vacuum process.
I think I don't know. I don't know the answer to that question. Maybe some molecules, maybe some. The question of whether
integration between the different processes. I don't know if that could be an advantage, but we can chat.
Yeah.
Okay. Sorry. Any further questions?
It's just a bit provocative. I mean, your center is called for quantum research and technology. Is there any association with qubit and kind of quantum computing kind of things where you may use some people think about this kind of multiple memory stations? Is there any way you may combine respectively your let's say, for example, your multi-level organic memory devices with any potential qubit technology?
Yeah. So I've been thinking about it, right? I mean, there's a school of thought that says that it'll be almost impossible to make a qubit out of an organic system.
Well, that's.
I mean, let's just take, I mean, which are the materials that are used for qubits today? I mean, diamond, okay, why diamond? Okay, first of all, diamond because Dubai temperature is very high. I mean, so essentially what happens is all the phonons and everything, right? The phonons play a pretty, negative role in when you build a phonon device. So phonons are a problem, and therefore you want to go with materials which are pretty hard and which have very high Dubai temperature. So organic materials right away, you got a problem with that because they just have so many excitation mechanisms in the system, right? All the vibration, rotation modes, and just there's too many interferences basically. So that's one problem. Second thing is the isotope effect, okay, basically. So you cannot have, essentially nuclear moment, finite nuclear moment nuclei in your host material. And that's a huge problem because it causes decoherence of the quantum state. Right? Okay. So that's one of the reasons why we proposed to cerium oxide as a host for quantum systems. Just recently, a paper just came out from Chicago and PNAS, basically showing that they examined 12,000 different materials for quantum qubits, and their conclusion was cerium oxide is numero uno. It was really funny. I mean, my student showed me the stuff, and I said, see, there is a moral and lesson for you that anytime you think of a great idea, there are 10 other guys who are thinking of the same idea. That's what I'm telling you. And they even published a paper before we could do anything, right?
No, when we spoke about cerium oxide.
Remember I'm telling you about
cerium oxide films.
Yeah. I mean, cerium oxide is an easy film to make. Yeah, it's a wonderful film to make by PLD, right? So it's an exciting system for us to study. It's really has got record coherence time basically. The cerium oxide that's predicted. So it's a wonderful system. Yeah. I'll give you that paper. It just came out. I just got it like 3 days ago.
Okay, thank you very much. Unfortunately, we have to wrap up, but thanks very much for all of these discussions. And like I said, you'll be around for a week and maybe can be available for discussions, especially on next Friday at White City then. So, and this afternoon for here at South Kent later on as well. So thank you very much. That was good.